Thanks for yes, sure, yes, and thanks a lot for staying with me for the second day. Yes, I will start. So the plan for today is. Yeah, so I will finish the job which was left yesterday. So I will give you the first non-trivial application of Bolobash lemma for graph algorithms, and then hopefully again, so I will speak about representative sets. I will speak about algorithms for computing representative sets, and if time allows, I hope to finish today with the longest path algorithm. But again, so this is again only the plan, and who knows where we will finish today. Okay, so reminder. So yesterday, the whole hour, I was speaking about Bolobash lemma, and this is the brief reminder. What is this lemma about? So we have M sets A, A1, A2, AM. All of the sets are of the same size, and we have M sets B's of size B, and these sets, they satisfy very specific conditions. So the first condition is that if I have two sets AI and BI, for every index I, these pairs should be disjoint. And then for any other pairs of indices, of non-equal indices, the set should intersect. And then what Bolobash lemma says that the number of such sets is always doesn't exceed A plus B, choose B. So this is the Bolobash lemma. And yesterday I stopped at the application on counting the number of minimal separators in the graph. So reminder, once again, what is a A-B separator? I have two vertices A and B, and then I said that a set of vertices in a graph is an A-B separator if this set of vertices separate vertices A and B. It means that if I remove the separator, then the vertices A and B will be different connected components, or there will be no path connecting A and B. Or equivalent formulation will be that every path from A and B should hit at least one vertex of the separator. So there are examples of three separators. So I have and then minimal separator is a separator which is inclusion minimal. So this on this example, this separator is not inclusion minimal. Okay, so this separator is not inclusion minimal, right? And why? Because basically, if I remove this vertex, then so I will obtain this separator, and this is still a separator which is contained in that. Or if I remove that vertex, I will obtain that separator. So, but the other two separators are inclusion minimals. And then the question is, how many minimal separators could be in an n-vertex graph? And the trivial bound is definitely at most 2 to the n, because vertex separator is a set of vertices. So if I try all possible vertex sets, I also will hit all possible separators. So it's definitely at most 2 to the n. So what I want to show, I want to use Bolobash lemma to show that every n-vertex graph has at most this number 1.6181, and this is a rounding, so there are this is a rational number, so there are more digits after 1 power n. So it's this amount of minimal separators. Okay, so but before applying Bolobash lemma, I have to make some combinatorial. I have to make some observations. It's just not follows for free. I have to do some job. Okay, so the first observation is that if every minimal UV separator is uniquely determined by the connected component containing the vertex Cu and by the connected component C of V of the graph obtained from G graph by removing the separator S. right? So how come and why it's like that, right? So basically, the observation here is the following: that if I have a minimal separator S, just I will make a notation here, spotlight. Yes. So if I take a minimal separator S, and then I take the component containing vertex U in the graph G minus S, and then I take all vertices adjacent to vertices of this component, so I take the open neighborhood of this component, then I will obtain again this separator S. And the same is for the second, so everything is symmetric here, and the same is for the second vertex and for the second component. So why this is so? Well, so we have to prove that the open neighborhood of the component Cu below is a subset of S. Well, why? Well, this is a separator, right? So if I take this at S, I remove it. This what remains is a component, right? And then, of course, every neighbor of the component should be in this separator S, because otherwise it's not a separator. Yes, and why every vertex of the separator belongs to the open neighborhood of a component? Well, just take any vertex X of this separator, and then I claim that there should be a vertex Y from the component Cu, which is adjacent to X. Why? Because if there's no such a vertex Y, right? What happens if I remove vertex X from the separator? It's easy to see that if there's no vertex Y adjacent to vertex X, if I remove vertex X from the separator, what remains will still be UV separator. But this will contradict that the separator is inclusion minimal, right? Because that's means that because of the minimality of the separator, there is always a vertex Y, which is in the component Cu, which is always adjacent to vertex X, and there is another vertex symmetrically. There is a vertex Z, which is also adjacent to vertex X. Right, which means that the open neighborhood of one component it fully covers the separator, and the neighborhood of the second component also fully cover the component. Right. So far it's just I'm using the property of the separator and the property of minimality. So let me just okay. So there's a chat. Okay. So the question is: can't a path from U to V pass through multiple vertices of S? Of course it can, right? But it doesn't contradict to anything, right? So what I said, so I just only say that there exists, so for any vertex of the separator, there is at least one neighbor on the left, and there's at least one neighbor to the right. Yes, but definitely any path could be hit in many places by the separator. That's perfectly fine. Yeah. Okay, so that was the observation, and actually by using this observation, I can go immediately below 2 to the n bound on the number of minimal separators. Okay, so let me just to show, I just fix the size p of the minimal separator S. I will fix the size of the component Q, right? And let me just assume that the component which contains U, Cu, is smaller than the component which contains the component which, or it's not bigger than the component which contains the vertex U, the component C of V, right? Well, everything is symmetric, right? So at least one of them should be at most than the other, right? Okay, so then the size of the smallest component is Q, the size of the separator is P, and now what I know, right? So how many components of size Q I have? N, choose Q, right? How many components or separators of size P I have? N, choose P. And again, so I either can guess, I can enumerate all sets of size P, but I also can guess, I can enumerate all sets of size Q, because again, every component, it's full component, it's fully characterized the minimal separator. So if you give me a set of vertices and say, oh, this is a component, then I just take, then I also can find the separator. I just take the neighbors of this component, and this is the minimal separator. Okay, so then I should take the minimum of these two things, but also the condition is the following, right? That this value P and Q, they are between 0 and n, where n is the number of vertices in the graph. And also well, so this is the size of the separator, and I have two components. So P plus 2Q should be at most n. And now it's just a pure optimization problem. And well, if you play a little bit with these numbers, well, it's not always easy to see what's happening here because it's a non-convex function, right? But just believe me that the optimum, so the maximum of this function is reached when all these guys P and Q are equal, and they are equal to n over 3 because of this condition. And then this value is equal to n, choose n over 3. And then, so if I do the Stirling approximation, this is a standard thing here, so I will obtain this number. So this number is better than 2 to the n, but I promised you to show that this number is 1.6 something. Okay? And now this is the moment where the Bolobash lemma comes into play. So any questions so far about this construction and about this bound? Good. Yes. Okay, so the crucial observation here is the following. So if I just take, so let me just count a very specific situation. So I just looking only for connected components of size P, exactly of size P. And I also looking for the minimal separators, sorry, minimum separators of size exactly P and connected components of size exactly Q. And then the crucial observation here is that this sets of components and the corresponding separators, that they satisfy the condition of Bolobash lemma. So why? Well, so if I take a separator Si, right, and I take the component, the corresponding component, right, of course, they do not intersect, right? Because what is the component? Component is a part of a connected part of a graph, which is obtained after I remove the separator from the graph, right? So they could not intersect. So for every index I, this the corresponding component and the corresponding separator, they do not intersect. However, if I take a different or components and separators with different indices, because the components are of equal size, so all of them are of size exactly Q. So if I and all of them contains the vertex U. So how many components of size Q which contains vertex U could be? Right? Well, there could be many of them, right? But if there are two, so if I take any two of these components and I take the neighborhood of these components, then this neighborhood would be different because these are different components. And this means that every minimal separator is the neighborhood of such component. So it means that for all indices I and j which are not equal, so the intersection of the separator and the component is non-empty. But then this is exactly the condition of the Bolobash lemma, and I know that the number of such sets M doesn't exceed P plus Q, choose P, right? I have components of size P, I have separators of size Q, and I have again, so then it's the number of all possible guys which satisfy this condition is at most P plus Q, just choose P. Okay, so now I have this knowledge and I can rewrite my formula, right? So now now instead of guessing all separators of size P or components of size Q, what I can do, right? I just can search for the minimum or for the maximum of the minimum of P plus Q, choose Q, where I run through the numbers P and Q, which again satisfy this condition that P and Q is between 0 and n, right? And also P plus 2Q is at most n. Yes, and now, so the previous worst case for this system, it was 1.888. So that was n choose 3. But now, if you play with the numbers, the worst case, now it becomes 2 to the n over 3, choose n over 3. And this is at most 1.6 to the n, right? And more precise calculation gives you 1.6181. And actually, maybe just a question, have you ever seen this number? So it's not just an arbitrary number. Exactly, yes, Mirza, yes, thank you very much. Yes, this is the golden ratio. And actually, yes, it appears, yeah, there is some magic why it appears. Definitely. So when you compute this number and you do this optimization, you play with Fibonacci numbers, and but you can also just run your favorite optimization, or you can write a program on Python, or you can run Maple to compute this number. But somehow this is a golden ratio. Yes, so we proved that, what we proved, right? We proved that for every pair of vertices U and V, and for every numbers P and Q, there are at most this number. Okay, yes, so again, so this, yes, so the question is, how do you find the optimal values for P and Q? So this is the question I hide under the carpet, right? So I say just this is a golden, and I say that you can use some, well, so the direct thing, so basically how we found, right? When we realized that this is when we realize what we want to optimize, we just run the, so okay, I will tell you the true story. So what we did, we just run Maple and we find this number, and then after some time we saw, oh, this is the golden ratio, right? And actually we counted up to 10 digits, and it still was golden ratio. And then I thought, okay, maybe we will be able to prove it analytically. And then but you have to play with binomial coefficients, and it's not rocket science, but so this is what I so if you want to play with this, please do it, or look at in our paper. But this is somehow, it's not so interesting, so I don't want to speak about this. Yes, but again, you're right. So it's when you look at the formula, it's not entirely clear. So why for this P and Q this should be the maximum of the formula, right? But please trust me here. This is okay. So what we showed, so we see that there are at most this number of minimal UV separators of size Q, and components of size P, right? But then, so because there are like n square pairs of vertices, and there are like n squares possible values for P and Q, right? So, and then, so I just bound this, but because this is the usual trick here, the power of a big O for the exponential functions, because yes, so what I write here is not 1.6181, but here is a rounding, so there are a bit more numbers here, right? And these more numbers here, they dominate any polynomial function here. So I can, well, so mathematically speaking, or this formula is not correct, right? So, but because this is not 1 point, but if you say this is a golden ratio here, then what the remainder in this number, they will, in the power n, they will dominate n to the 4, right? So this is okay. So this is the bound of the minimal separators. And actually, so why minimal separators are useful? Well, there, so to count the number of minimal separators, or to enumerate all of them, it's quite, it appears to be as an important subroutine in for doing several algorithms, which involves algorithms computing potential maximum clicks. And actually this leads to a lot of many fast exact algorithms. If you want to compute independent set in a graph, if you want to compute maximum induced forest, if you want to compute a graph of bounded trivets, to compute the film of the graph. So there are a lot of different problems, and this type of subroutine, computing of minimal separators, is important subroutine in all these algorithms. So it's not again, it's not a pure of mathematical curiosity how many objects are in a in a graph. Okay, and just immediately open question, and this is like what I really like in this area of research, right? So there are a lot of open problems which you can explain after a few minutes of talking to people, and this seems to be quite difficult, but still quite interesting open problem. So what we know, right? So I just show you that the number of minimal separators doesn't exceed this number. Okay, so there is a slightly better, so the algorithm or the proof which I gave you is like n to the 4, but it's possible to do it with slightly different arguments, even to decrease the polynomial here. But again, the best lower bound, so we know examples of a graph which contains this like 1.44, okay, 2 to the, oh sorry, 1.4457 should be here to the n, right? And actually, I really don't know what is the right bound. So for a long time, I believe that the wrong, that the correct bound is 3 power n over 3, and which is 1.442 to the n. But apparently, as this paper shows, it's not true. And then what is really true, it's really, but already for quite a few years, nobody is able to improve anything to say, so where the true value lies. So if you are able to improve upper bound or improve a lower bound, each of these results will be a nice research paper. So just, so if you have ideas or just try to play with this. Okay, and I continue again with the cosmonauts, and but again, so the right time to ask questions about Bolobash lemma and about minimal separators. Okay, is that no, so yes, it's 3 power 1 over 3, yeah. Okay, so there is a question and there is an answer to this question. Okay, so thanks, that's the best output. Okay, so once again, so the main idea behind algorithmic usage of Bolobash lemma, it's called, it's based on representative sets or representative families. It's again, I already pronounced this idea once, but let me just repeat it once again. So what's happening? So if I have a family of sets A1 up to AM, and this is a minimal family of sets of size A, minimal subject to the following property. So if I take any set B of size B, there should be at least one set AI which is disjoint with B. Then, because this set is minimal, for every set AI, I can find a set BI of size B, which is disjoint with AI and intersecting all other sets AJ. So just let me just give an example, right? So that will be the, okay, so initially I tried to build an example with the cosmonauts, but because I have 20 people and I have a set of size 6 there, then I realized quite soon that this example will be quite difficult to make, right? So I make a simple example. So I have a set, a universal set of size 5 from 1 to 5. And then the sizes of sets A are 2, and the sizes of sets B are also 2, right? And let me just take the family of these sets. It's just, it's not all pairs of sets of size 2, right? But if you play with the sets, you will see this, the following property. So imagine, so just I have the set, and then you are advisory and you just play adversary and you play against me, right? And you want to play the following game. You just give me any pair of elements. You give me any set B of size 2, and then you will say, oh, please find me a set from your family which doesn't intersect my, right? Okay, and here it's again, so for if I give you 1, 2, then there is a set, for example, 3, 4, which does not intersect with 1, 2. If I attack with 1, 3, then I can defend with 2, 4, right? And etc. Right? Now the question is this set A minimal with this property? Or I can delete some pairs from the set and still will have exactly the same property. Okay, so for example, what's happening? Let's take a look at the pair 1, 2. So the pairs from here that do not intersect 1, 2 are 3, 4, 3, 5, and 4, 5. All right. But now for the set 3, 4, there is also the set 2, 5, which doesn't intersect it. For the set 3, 5, there is also the set 1, 4, which doesn't intersect it. And for the set 4, 5, there is a set 2, 3, which doesn't intersect it. Right? So this means that if I remove the set 1, 2 from the set, the remaining family of sets, they still satisfy this property that for any attack from the set B, there always will be somebody from here which can defend this set, right? And this is exactly the property which I'm and this is exactly the property which I discussed here, right? So if I have a minimal family of the sets, then for every set in the family, there is always a set outside it which is disjoint. But because of the minimality, this should be unique representative of this set. So it means that the set, the corresponding set BI should intersect all other members of the family, of this family. So in other words, what I'm saying, that if I have a minimal family of sets with this property, then this family of sets should satisfy with some set of BIs. Together, they should satisfy the condition of the Bolobash lemma. And this will be the game I will be playing again and again with all these representative sets. Any questions? Okay, so the question is, the problem is interesting only for A plus B at most X, right? Exactly, yeah, yes, and yes, but also the Bolobash lemma is also, it plays only for, yes, for these things. So you can, for algorithms, you can also adjust the things, but you have to do some adjustments. Yes, so it's okay. So yes, again, so yes, so summarizing, if I have this minimal properties, set with these minimal properties, then actually this family of sets should satisfy the conditions of the Bolobash lemma for some family of sets B's. And then the cardinality of the set should always be at most A plus B, choose B. Okay, everything is so nice, but now we speak about algorithms. And here the important question is immediate, right? So if I give you a set of family of sets, right, and I want you to compute a minimum subfamily of the sets which satisfy the same, satisfy this property, how efficiently to compute such a family? And this is exactly, so the question is how to compute representative sets. And so, but let me just once again to repeat again the same thing, because this is important to understand it for the remaining part of the lectures. Okay, so I have a family set, F of sets A1 to AM, and each set of size A. And when, so what I want to do, yes, yes, the question is family sizes equal? Yes, exactly. All sizes for A are equal, and B, but A is not equal to B, right? So I have a family of sets A, all of them of the same size A. And when the new set B of size B arrives, so the question which I want to ask, right, if there is a set from my family F, which is disjoint from B, right? This is just the only question that we view it as a query, right? Or the game Alice and Bob are playing, right? And Alice just had a family of sets, but the only thing what she remember, if Bob sends the set B, so then there always should be an answer which is disjoint with what Bob sent. Okay, so and then do we need to keep all sets in this family? And again, so what we see, right, so that the set AI is crucial only if there is a set BI of size B, which is disjoint from this set and which intersects all other sets I in the family. And then by Bolabash lemma, so if all sets in the set F are necessary to satisfy this or to play this game, then always the number of the sets is at most A plus B, choose B. Okay, so then this it brings to the definition. So I have a family F of sets of A sets, the family of sets of size A, and then I say that the subset F prime of F B represents F if for every set B of size B such that there exists a set from F which is disjoint from B, there always exists a set A prime from the family F prime which is also disjoint with B. Right? And with our discussions from Bolabash lemma, it follows that for every set F, there is always a B representative family of F, whose size is at most A plus B, choose B. Okay, so we know that such family exists, but how to find such a set F prime? And the problem here is that if you look at the definition, right? So the definition says that so the family represents set that if you take any set B, then there should be a set A which is disjoint from B. So we know A, and we know the size of B, but we don't know all sets in B. It could be so because the number of sets in B could be too many, right? To design an efficient algorithms, and this is the problem, right? So we don't know the family B, so it's hard to say which sets are necessary to keep this condition. Or okay, so the first algorithm, or so the first attempt to compute representative sets efficiently is based on the algorithm for de-heating set problem. So a reminder, what is a de-heating set problem? So I have a universe U, I have a family S of sets of size at most D over this universe, and I have an integer K. Or in other words, you can say you have a set of U vertices, and you have a hypergraph where every hyper H is of size exactly D. This is the same thing. And then the question is if there exists a subset of vertices X of size K, which hits every member of the family of the set of hyper, or if there is a hitting set of size K, which hits all hyper edges of the hypergraph. So in this example, so I have a family of sets of size 3. So I have 4 families. So this example, it has hitting set of size 2. So vertices B and G, they intersect together all sets or all sets in the family. So this is called the so D heating set D is the size of the sets, and heating sets, yes, and D heating set is solvable in time D power K times the number of sets in the family. So this is the fact, and actually the algorithm is yes, family sizes yes, and yeah, and the algorithm is again a branching arguments in this. So what's happening here, right? So I just take any set in the family. This set is of size D, and I know that this set should be heated, or should contain at least one vertex in the heated set, right? So I try all D vertices as a potential heating set, right? So what I'm doing, I just I branch into at most D smaller sub-problems, right? In each of these sub-problem, I remove the vertex D from the set, and also I remove all hyper edges or all sets which are heated by this vertex, right? So, and because I'm looking for a set of size at most K, so the depth of the recursion is at most K. So I have this recursion tree. Degree is at most D. The depth is at most K. So this means, and at every step, I perform a polynomial time, right? So then it means that the running time of this algorithm is proportional to the size of the tree, D power K, and times some polynomial, actually linear time on the size of the problem. Right. So now we are ready to have the first algorithm for computing representative sets, right? So I know that once again, I know that for every family F, there exists a family F prime of size at most A plus B choose B, that B represents family B. So how to compute this family F prime? Well, so what I'm doing, I'm just, it's a kind of greedy approach, which at every step of my greedy step involves solution to the heating set problem. So what I'm doing, so I just go through all sets in the family. I take the set AI, and I want to decide if I want to keep the set AI in the representative family, or I want just forget about it, throw it away. So I take this set, and then I just what I'm doing, I remove the elements of AI from the set, from all sets in the family F. I obtain some smaller family of sets, and for this family, I check if this family has a heating set B of size small b. Right. Well, again, so I'm just searching for the set AI. I'm searching for the set BI, which doesn't intersect BI and which intersect all other sets in the family, right? So this is exactly so. If such set, if there's no such a set, then I just delete AI, and if I found such set, right, I can say, oh, this is exactly the BI which is paired with the AI because it doesn't intersect AI and it intersects all other sets, right? I continue this way. So at the end, what I do, I construct a family of sets, right? AIs and BIs, and I know that for every index I, AI and BI are disjoint, and I also know that for every I not equal to J, AI, or sorry, BJ intersect AI, right? But this is again, and this is again the condition of the Bolobash lemma. So I know that the size of the set which I will obtain by this argument will be at most A plus B choose B. Yes, and also I know that this is the set that will be represented. So as we discussed, so that will be the representative set. Yes. So the question is why AI and BI are disjoint again. So what I'm doing, so I'm taking the set AI, and I remove all elements of AI just for a minute, right? I remove them from a set F. I construct a new set, and then I just compute a heating set for this of size B for in the set F. So the set BI, it cannot contain elements of AI because it's just a heating set for the instance where the universe doesn't contain the elements of AI, right? Yeah. Yeah. So the running time is this one. Yes. Thanks. Okay, so the running time is okay. It's f square but f square, you can probably make it linear to f. Yes, but the thing which I do not like is a power b. Right, and so the question is actually, is this running time even a polynomial? I would still what I want, I want to have a polynomial time algorithm right at the end, right, and to compute representative sets. Okay, so what we can do, so what we can assume, right? So a plus b choose b. This value, because it's we're looking for some subsets of set f, so this always doesn't exceed the cardinality of f. Right, but the running time of the algorithm, which I would be happy with, will be the running time of the algorithm which runs in time polynomial in a plus b choose b and polynomial in f. Right, but a power b, it's not a polynomial of this function. Why? Just well, for some values of b, it's a polynomial. But for example, if a here is a small constant, for example, if a is equal to 2, and for example, if b is equal to n half, right, and say f is equal also to n, then a plus b, or say f is equal to like n to the 5, for example. Then a plus b choose b. This is a n plus 2. Let me just write it. So then it's this is n plus 2. What I'm saying. This is like, for example, n half plus 2 choose 2. So this is something of order like n half 2 square, right? So it's polynomial of n. But this value is something like 2 to the, sorry, 2 to the n half, right? So this bound is not polynomial. So it's so okay. Let's try another approach. So this time I will give you a set algorithm which outputs a representative set of size 2 power a plus b log n. In time, the size of the family times 2 to the a plus b log n. Again, this running time and this size, it's not polynomial again of the input size. However, already this type of algorithm, it will be useful for some algorithmic applications. And actually, I will be using this for algorithmic applications when a is roughly equal to b, and this is okay. Okay, this algorithm, so yes, once again, I want to have an algorithm which constructs a b representative set f prime of size 2 power a plus b logarithm n, and the running time of this algorithm will be polynomial in f times 2 to the a plus b times logarithm of n. Okay, and the algorithm is based on the notion of a universal k-universal family. And the main idea or intuition behind the algorithm, so if you remember how we proved the Bolobash lemma, we were using separation permutations. It's quite difficult to use permutations algorithmically, but somehow what I want to do, I want to separate partitions, nothing else, right? So, and for separating partitions, there are very nice tools which are called k-universal families, which are quite well understood and developed in computer science. So k-universal family for universe U of size n is a family of functions from f1 to ft, and these functions, they map the universe into two colors, red and blue. And the condition is that if I take any subset of the universe of size k, and I take any coloring of set S in two colors, then actually there should be at least one of the functions fi which colors the set exactly the same way. right? So for example, in this example, I have universe of 3 elements. I have k equal to 2, and this is the set of my, this is my universal family. So if you, for example, if you take any subset of size 2, for example, B and C, and I take coloring of B in red and red, well, this coloring is here, it exists here. Or if I take coloring of A and C, A in red and C in blue, okay, this exists in my table here and here. And some colorings could exist in, okay, so here, yeah, so this is, yeah. And you see that the number of these functions, even on these examples, it's so the number of all subsets of size 2 of these 3 sets should be at least, yeah. So yeah, so should be definitely larger than 4, right? And the famous result of Naur, Schulman, and Srinivasan from 1995, it actually is give a construction that for every k, we can construct a k universal family of size 2 power k plus small o of k logarithm of n in time 2 to the k plus small o of k n times log n. That I will be just using. So there are a lot of different constructions of universal families by now. I just will take this one. It will serve for my purposes quite well. Okay, so then so the algorithm. So I have a set of A sets, and I have a number B, and I want to compute A plus B universal a set of functions f1 of t, such that t is a plus b plus small of a plus b plus log n, right? I'm just using the Naur Schulman Srinivasan algorithm as a black box for that, right? And then what I'm doing. So I just label all functions fi's in the beginning as unused. And the set f prime is empty. Right? And now I start to fill the set f prime the following way. So I just take ai, and if there is some unused function fj, which colors the set ai in red, then I add ai to the family f prime. And I mark the function fj as the used one. And then I output the family f prime, right? So this is any questions about the algorithm? Okay. Okay, so yeah, so but yes, so we have an algorithm. So as usual in the algorithms class, right? I should explain first of all what is the running time of the algorithm, and actually why the algorithm computes what it's supposed to compute, right? Okay, so yes, first of all, what is the size of the set which is its output, right? Okay, for every function fi, it adds at most one set, right? And since the number of functions was 2 to the power a plus b, so was at most this number, so the size of the set I obtain is of this size. So this set is okay. And also for the running time again, so the running time of the algorithm is just what I'm doing. I compute the universal functions, right? It takes time, and then after that, I'm just going for all sets in I and for all sets in fj. So it's like it's polynomial in the size of the functions and in the size of the family f. Okay, so the most important thing. So I obtain a set f prime. So why the set f prime? It's a b represent the set f. Well, suppose yes. So yeah. So let's prove it. Suppose there exists a set AI in set F and a set B such that AI is disjoint with B, right? And then I have to show that there's always some set in F prime which is also disjoint with B. Okay, so because the functions are universal, right? I know that at least some function fj is, or because the functions a plus b universal, right? So for any set of size a plus b, there's and for any coloring of the set of size a plus b, there should be a function in my set which do this coloring, right? So then it means that there should be a function fj which colors ai red and b blue, right? Okay, so if the set AI doesn't belong to the representative, or sorry, it's not representative family yet, I still didn't prove it, right? So if AI doesn't belong to the constructed family F prime, so the only reason, right, is it was not added to the set just because the function fj was already used before. But okay, but if the function fj was used before, well, so this function fj, it was used on some set aj, which was colored red, right? By definition, right? So this set aj was colored red, right? So then this function fj, so it colors the set aj in red, right? But it also colors the set blue, B in blue, right? Because it's again, it's colors AI in red and B in blue. So it's colors AJ in red, but B in blue. So AJ is colored in red, B is colored in blue, which means that these sets, they do not intersect. But these sets, they do not intersect, which means that this family F prime contains the set AJ, which doesn't intersect B. So this means that the family F prime is a representative set. Okay, so just to conclude, so this is the algorithm which computes a representative set of size 2 to the power a plus b, roughly, log n, and the running time is 2a plus b. Okay, so this is, again, this running time is not the best what we can or what we know about. So basically, it's possible to improve this running time, and with so the best known algorithm I know is the algorithm which constructs a set of size a plus b choose b times 2 to the or small o of a plus b, and the running time is this one. And here it's not a plus b choose b, it's a plus b divided by b, and by playing with these numbers, you can obtain different running times. And this is also could be I probably, if time allows, I will speak a little bit about this type of algorithms on Friday. But again, so this algorithm is way more complicated. So the idea is, again, very similar, but you have to do a much more careful work to play with different things, and it's yeah, it's just way more complicated. So you have to really you cannot use the black box of universal families. You have to reopen it, unfortunately. Okay, and what I want to do tomorrow. So tomorrow I want you to give the first real algorithmic application. So yes, so this is the algorithm for computing representative sets, and actually this is this algorithm is as if you assume the construction of Naur, Schulman, and Srinivasan as the black box. Already with this not the best algorithm for representative sets, you still can do quite amazing things. And our first example will be about the longest path problem. So it's a generalization of the Hamiltonian cycle. So the longest path problem is I have a graph, I have an integer k, and I ask if there exists a path of length at least k, or the path which contains at least k vertices. And so yes, so we have an algorithm which has which computes representative sets of this size and with this running time. And actually, what I will explain you how to do the algorithm solving longest path in time 4 to the k plus small o of k times some polynomial of n. right? And so far, so so if you never saw this type of algorithms, just think about this that way. So you want to find a path of length k, if there exists one in a graph. So how you will do it? So if you are just do it very naively, right? You just want to try all possible sets of ages, right? At most k minus 1 ages. You try them and see if your attempt constructs a path. But this running time will be n power k, right? This is simple. Now just try to think, can you construct an algorithm whose running time is, for example, k factorial times some polynomial of n, or k power k some polynomial of n. Just play with this, and if you succeed, you will be great. If you do not succeed, nothing terrible in that, because actually very, very clever people spend quite significant amount of time on proving such type of things. And actually, even so, the algorithm of k to the k, it requires some techniques and some tools. But what I will give you a quite simple, well, dynamic programming algorithm at the end, which computes the not even in k factorial, not even k to the k, but in 4 to the k, in single exponential in k running time. And actually, if you know how the, okay, as a spoiler, so if you know how the Held and Karp algorithm from 1960s for the which runs into to the end, how this algorithm, dynamic programming algorithm works, now you have all knowledge to construct the algorithm which runs in time 4 to the k. But I will start from that tomorrow. Yes, any other questions, please? Okay, so if there's no questions, I just, as usual, I can have only one of the two conclusions, right? The first one, I was so good and I explained everything so clear, right? That everyone understands everything and everybody, but usually it's not true, right? So does it mean that just nobody understands anything? Or things are somewhere in between?
Probably somewhere in between. Actually, do you mind a question?
Yeah.
I kind of forgot somewhere in the middle. You were using the Balabas lemma for a fact, and I wasn't sure that. I think you were using it for like. It was using the Balabas lemma, but I wasn't sure that the size, like the number of A's and number of B's is actually equal. And I think someone else also asked the same question.
Okay, so equal, okay, so A is not necessarily equal to B, right? It could be equal to B. So that was your question, right?
No, I think in one of your proofs, like so in Balabas lemma, you have to have that like number of sets of A have to be M and number of sets of B have to be M. Like the sizes, numbers should be equal of those sets.
Okay,
and like
okay, I got your question. Yes. So yes, so I show you two variants of the lemma, right? In one variant of the lemma, all sets A were of the same size, and all sets B were of the same size, small a and small b. And then I also told you, okay, so there is even a slightly more general variant of lemma, right, where the sets A could be of different sizes and the sets B also could be of different sizes. And then I show you actually that why one variant implies the other. And then, but then I also was saying that yes, one variant is more general, but for algorithmic purposes, actually, we use only the variant where all sets are equal. right? All A's are equal and all B's are also equal. Right? And this is yes, so, well, I call it also Bolobash lemma. You can call it the weak version of Bolobash lemma. But so that was the question, right?
I think it was a little bit different, but I'll find a slide later and tell you later if you give me a couple of minutes.
Okay. Yeah. Yeah.
I'm afraid the question was about the sizes of families of all A and all B. Just because of the notation, you write sometimes A sub I equals B sub I. So it could mean that the number of different sets A is the same as the number of different sets B, which is not the case in general.
This is you mean the cardinality of the family.
Yeah. That's how I understood the question.
Yes. That's a good. Okay, now I understand. Okay, at least now, sorry. That's yes. Now I understand the question, right? Okay. So yes. So what's happening here? Again, in Balabash lemma, we speak about two families of sets, right? And they are of the same cardinality, right? Its cardinality is M. The number of sets A's of A's is M, and the number of B's is also M. But now, so when we start speaking about representative sets, right? I just have a family of A, and I have no idea what is the family B. So I always assume this is the worst situation, that any subset of size B could be in the family B. But then the only property which I care about, that when the set B arrives, there should be someone from the set A which is disjoint from that. And then I'm asking what is the minimal size of the set of the family, yes, and I'm using the Bolobash lemma, which says about the number of pairs. But so the way I'm using it, it's so the way I just say, okay, if the set is minimal, then I can construct the set of pairs. So Bolobash lemma, it speaks about this the pairs of sets, and here about two families of sets, and the cardinality of these families are the same. But when I speak about representative sets, right? So there is only one set there, and the only thing which I want to do, I want to make the set minimal. So there is no cardinality. So and the only thing I care about the cardinality of this minimal set. So this is them.
Oh, okay, thank you.
Yeah, so there's also a question, would the color coding technique work for longest path problem and have the same running time? The first thing is, if you care about the single exponential thing, yes, but the running time of the color coding, so it will be twice e power k, which will be worse, right? So this is so this for to the k, it's already better than color coding technique. So it's but again, so color coding, I wouldn't ask you to invent color coding like an exercise, please. This is it's you already use some knowledge which which is good, but so. Yes, there was a 2 to the yes, but 2 to the O of k. Yes, the question is, wasn't it 2 to the power of k something? Yes, definitely. But what is hidden in the big O, right? It's in the exponent, right? So 100 power k also could be. And here the game for the longest path, the game is what is the best exponent? And actually there was several breakthroughs. There was a color coding. I will talk about this tomorrow also. But there was several breakthroughs, and then there was like a amazing result of Ryan Williams, who gave randomized algorithms constructing the longest path in time 2 to the k. And then actually there was even more amazing result of Björklund, which managed to go below 2 to the k. Right, but again, so there are these algorithms are much more advanced. Yeah, so definitely no. 4 to the k, of course, it's not the best state of the art algorithm. But this is what you can, the impressive thing here is that Actually, this is the algorithm which you can do just knowing the representative sets and nothing else. Yes, but you can de-randomize it. So it's like these things are very well known. Yes, so universal families, that's how to de-randomize it. And actually, it's also the color coding, right? It's a randomized algorithm, but again, you use universal families to de-randomize the color coding. So it's good. So any other questions? Okay, then have a nice break and see you tomorrow. Bye.
Thank you very much.